So tell us about
Yeah.
the donkey car. This is what you're sort of organizing all these events around.
Yeah.
Yes, yeah. Uh, Jackie and me, we involved in the donkey car very early from 2019, maybe earlier. And the donkey car is a famous, self-driving solutions for the RC cars. And you can see on the left side, that this is the original design of a donkey car. And for the right side, here's a local design named Pyracer Pro from
Mm.
Wheelchair. Yeah, and this kind of developing kit help us to build our donkey car very very easily, and because we can share all this software and mechanical design, that lots of members can come to enjoy the happiness about the donkey car.
Yeah. And
Yeah.
tell us about this Pyracer Pro from Waveshare.
Yeah. You know, we are standing on the shoulder of giants
Mm.
and make some improvements, just such as localization, rapid optimization, and so on. And this picture is our hardware design for donkey car. Because
So,
the donkey car is made up of several components, such as camera, Raspberry Pi, batteries, servo driver board, and RC receiver, ESC controller, and brush motor, and so on. So we put them together to build our own race car.
I'm
So
interested in so one feature of the original that I've been to a couple of smart car racing days in the Bay Area, and I noticed that there were actually a lot of times when the cars would run into each other, and that's partly why I think they have this like armor structure over the top. Like it holds the camera, but it's also kind of like protecting it. And I wonder if you
yeah,
experience those same problems with people running into each other and colliding, and maybe you don't. So maybe you don't need that armor, but otherwise, are you thinking about adding it? Adding it?
yeah, we
Yeah.
are going to adding some armor
Nice.
due to we always crashing together
Yes.
because
Yeah.
donkey car is uh, is not notoriously stubborn,
Mm-hmm.
always go straight or hit something and always
Hmm.
trying to get over it.
I think that's part of the fun of this whole thing as well, is that it's more interesting than just typing on something. You get to see stuff like like do completely unexpected actions from these robots,
Yeah,
and just it's so fun to watch.
yeah, it's always staring around. If you interrupt the camera's feed, you may get different result. The
Yeah,
car will go straight or go left or right. You never
you never
can
know.
predict
That's
the
so good.
direction. So it's very funny.
Mm. And you train it by running it a bunch of times around the track manually, right? You drive it around and then it sort of
Right,
trains
right.
this model. Tell us about that.
Uh, yes, as we know, the donkey card, uh, but not owning hardware, also, sorry for that.
It's cool.
Not owning hardware, but also
Mm.
software. So as to software architecture, it includes RC car, Raspberry Pi, and Python libraries such as Tornado, Keras, TensorFlow, OpenCV, and so on. So all of this technique stack, we them together and build uh, this donkey car software environment. And the donkey car will gather information from the camera. Um, you know, uh, Once it gets the picture of the road or the map, it will store into a in a tab. And the data set includes image array, normalized steering and throttle data, and those data will be stored in a tab. We call tab, and then we train a model by using those data in that tab. And the last step is to let the donkey car run in autopilot mode by using the model we trained. So it's the entire operation process is very simple. So we shared our experience to the people who in the community, and they can find it's very easy to deploy the donkey car to their device.
Cool.
So
on all these different model formats as well, depending on what people's personal preferences are, they can use any of these different formats. It's very cool.
Yeah, but the entire operation process is it's the same. It's simple. You get you collect the enough data, and you train it, and then you drive the donkey car.
Yeah, just like that.
Follow the loop.
Yeah, this is the very first videos that we are training the donkey car. Yeah, you can see it's very hard to control. Most of the time, it's go out of the track, and you have to put it back. And you see, it stopped. We don't know why. Maybe this is the reason it's called it's named donkey. Yeah, but donkey is a very
stubborn. Yeah,
there's stuff one that he will persist on his track again. Yeah. And this video is from one of our members outside Shanghai, and he just sent how he trained these cars and what problems he had. So we can chat with each other, we can share our experience. That's why our community grows very fast, because we have a community that all the members will help each other.
Yeah. And you've mentioned this combination of helping each other and competition that seems like a really rich combination.
Yeah, yes.
We also share models and some experience in donkey car, something
all kinds of stuff going on, including this interview. DFROBOT.com sells lots of amazing products for robotics, and I should mention that they have a really wonderful documentation section. Just like all the products have these wonderful wikis with really in-depth getting started information, all kinds of good stuff there, plus cool products like this. Oh, and the Gravity series, which is similar to the other I2C plug-and-play series like Stemma and Quick and things like that, and Grove. There's a community on dfrobot.com. You have Mushroom Cloud Makerspace's Pi Day GitHub repo. I believe this would be part of what you were doing for Pi Day this year.
Yeah, it's
devices. Good stuff. Oh, this is a little bit older, but still cool stuff going on GitHub. You can find out information about the Donkey Car and the Pi Racer Pro from Waveshare. These are the two cars that we mentioned earlier. But also, I can't let you get away without mentioning this. You built a version of the Donkey Car called the Panda Car. Is that right?
Yeah, this is our secret program.
Yeah.
Oh, maybe I shouldn't have mentioned it, but I thought it was cool. And maybe we'll see more about that in the future someday.
Yeah, we will
Yeah.
share you in the next talk. That okay.
Cool.
Yeah, because we are busy developing this car. We do lots of software and hardware, modification that to enable that the Lati Panda to be a main controller of Donkey Car. And this Lati Panda is so powerful that we are very confident that we will win lots of racing game in the future.
Awesome.
Yeah.
We'll see how it stacks up against the Pi and even the Jetson, maybe. Great.
Yeah.
That's
Just
besides I just had these videos left. So yeah, again, everyone go follow DFRobot on their Twitter. We can drop some more links afterwards in the description.
Yeah. Thank you, Alex. Yeah, that's a great chance that we got
community to build a Donkey Car.
Awesome.
And it's so great to meet so many people who share the same interest here.
You've also got this.
Yeah. This is showed. Let's finish the video.
Sure. Safety helmet with intelligent embedded lighting device.
Yes.
This is so cool.
Yeah, we joined the Junction 2021 Worldwide Hackathon and won the out of box.
More cool stuff.
Yeah, this is my turn. Yeah, okay.
Before we begin, we will need to install Docker on a Linux host machine. Once Docker is installed, we will pull a container image which includes all dependencies necessary for building and running a Matter virtual device. Windows and macOS computers are currently not supported by this Docker installation. Instructions for manually installing and building Matter without the container image can be found in the Matter documentation. Installing Docker is not covered by this video. Please refer to the Docker documentation to install Docker on your Linux system. Now that Docker is installed, we may pull the virtual device image. In this case, we are pulling the image from Google Cloud Container Registry. Please refer to the published code lab for the latest URL of the image. In our video, the Docker image already exists in the local cache, and the pull operation completes quickly. However, expect that this step may take a few minutes to complete when run for the first time. Before starting a container, we run the xhost command. This allows the X Windows system to receive connections from localhost on port 1000. Our container will use this address to provide graphical user interfaces. Now, we will run a container using the pulled image by providing 3 arguments to the docker run command. --IPC equals host allows Docker to share the inter-process communication namespace with your host machine. --net equal host allows Docker to use the host's network stack inside the container. This is necessary to export display. Finally, -E exports your host's display environment variable to the container. Xclient programs running in the container will then connect to your host's X server, thus providing graphical user interfaces. This is important to run the Zap tool for editing Matter clusters. We will need to execute commands from within the container to build and run our virtual device. In a second terminal window, open another interactive terminal session in the container by executing bash in the docker exec command. Note that the -IT option runs Docker with an interactive terminal instead of in a background process. Now that we have completed the setup of our virtual device container, we may begin building our Matter device. All Matter examples are placed in the examples directory located within the root of the GitHub repository. There are several samples available, but our focus in this video will be on Chef. Chef is a sample app that provides a terminal interface and wrapping features similar to those found in the app located at examples/shell. It is also a script that conveniently encapsulates several of the common tasks necessary for development into a single command. We will now execute Chef to create our example device. Chef has several options that can be viewed by running the script with the -H option. Taking a closer look at the options we are using in this example, we find -D, which defines the input device type. We have chosen lighting, which is a single color light bulb. -Z invokes the Zap tool. This generates source files that implement the specified device type. Zap automatically creates code for our build. This code defines the light, being the data model, and its interaction with other devices, the interaction model. -B builds our device. -R is optional. This option enables RPCs on the virtual device so that other components, such as a graphical user interface, can communicate with it. Finally, -T is the target platform. Chef supports builds targeting Linux and some physical chipsets. Device builds targeting Linux may be run by executing the application located in the Linux build output directory. We will now execute the application. Upon execution, we are prompted to enter a Matter shell. Once in the Matter shell, we run the command onboarding codes on network to retrieve setup information necessary for commissioning our device over IP. This is one of several commands available in Matter shell which allow us to analyze the state of our device. We will leave our device running. To ensure our device is accessible, we will disable our firewall. If you wish to leave your firewall running, allow list TCP and UDP connections to port 5540. The Google Home Developer Center console is a web application which centralizes integrations with Google Home on Matter, as well as Smart Home and Local Home. Any Matter device that has gone through Matter certification works with Google Home. During development, we will create a project which provides additional context for the device we are developing. After our device is certified and we launch our project, the Google Home console will remain our hub for all of the additional features Google Home offers to Matter devices. On the Manage Projects page of the Google Home Developer Center console, we select Create a Project. We choose the option New Project and name our project Matter-Test. We open our new project and select Add Matter Integration. The virtual device we built previously was a lighting example. Respectively, we will name our new device integration Matter Light and select the device type Light. Finally, we must now enter the vendor ID and product ID. We populate vendor ID with 0xFFF1 and product ID with 0x8000. Note that the vendor IDs from 0xFFF1 through 0xFFF4 are reserved for testing. Before launching a product, you'll need to apply for a vendor ID from the Connected Standards Alliance. Off-screen, we will reboot our hub to ensure that it receives the most recent Actions project configuration. If you need to change the vendor ID or product ID later, please reboot your hub again after saving the project. The Virtual Device Controller is a standalone application that provides a graphical user interface to control and display the states of Matter virtual devices. The device controller issues remote procedure calls to Matter devices in our development environment. For the purpose of example, we will demonstrate installation in our environment. We begin by cloning the Git repository of the device controller. Please refer to the published code lab for the latest URL of the Virtual Device Controller. Once our clone operation is complete, we install dependencies and build the application. We will launch the newly built device controller by running electron main.js. The virtual device controller has two options at startup. --s followed by host:/port tells the controller to connect to a virtual device's network socket at the specified host and port. --d followed by a serial port file address, such as dev tty usb 0, tells the device controller to connect to a physical device over the specified serial port. It is also possible to launch the device controller with no option specified. Under these circumstances, the device controller will default to the network socket option using port 33,000 and host localhost. Observing the virtual device controller's interface, we are treated to a complete representation of our virtual device's state along with facilities for updating that state. Each time we update the light's switch, brightness, or color setting, the device controller will send a remote procedure call to our virtual device. Once every second, the device controller will poll the device state and refresh the interface accordingly. Let's observe the device controller's behavior when we control our device with the Google Home app. You'll notice that the switch on the device controller interface updates shortly after the light's state is toggled in the Home app. Conveniently, we may also retrieve the QR code used in our virtual device's commissioning flow from the virtual device controller interface. We will open the QR code for our virtual device in this example and leave it available for our next step. We will now commission our virtual device. Before commissioning our device, we will need to verify that the following steps are complete. a Google Home Mini, Google Nest Mini, or Nest Hub second generation device, our hub, is in the home network. Our device is configured in the Google Home Developer Console, as we executed previously. Our hub is paired with the same Google account we used to sign in on the Google Home Developer Console. Our hub is on the same Wi-Fi network as the computer we are using to run our virtual Matter device. And finally, our hub is in the same structure we are using on our Google Home app. Structure is the house on the Google Home graph. We will now turn our attention to the Google Home app. To begin commissioning our device, we tap the plus icon in the upper left corner. Next, we select Setup Device and New Device. We select the home to commission our new device into and tap Next. The app begins scanning. We now choose the option Chip Device. Depending on when you are viewing this video, look for an option that says Matter Device in the event that you do not see an option for Chip Device. We just scanned our virtual device's QR code. You can retrieve this QR code from the virtual device controller as seen previously. You can also retrieve the QR code from a web page at the link seen below in our virtual device's terminal output at startup. Let's observe from the virtual device side as the commissioning process completes. Our virtual device has been successfully commissioned into our home. We will name our new device Office Lite and test Control. The Google Home extension for VS Code offers features and tools useful when developing Matter devices. Note that the installation of VS Code and the Google Home extension is not covered in this video. Let's take a moment to examine the Google Home extension for VS Code. We select the Google Home icon on VS Code's activity bar. We now select our project, Matter-Test. In the Quick Access menu, we select Resources. This displays links to resources helpful throughout our development within the Google Home ecosystem. We will turn our attention to the Google Assistant Simulator in the lower left of the screen. Issuing text commands in the Assistant Simulator performs the same operations as voice commands issued to the Google Home Assistant on our hub or phone. In our example, we will test the command Turn on the light, which updates the state of our virtual device. Returning to the Quick Access menu, we select the option Cloud Logging. This opens the Cloud Logging Logs viewer, which contains a record of messages flowing between Assistant and our device. Expanding the different log entries to view their full content, we can quickly locate the success log for our previous intent whilst turning on the light. We now return to the Resources tab and select the Home Graph viewer. The Home Graph viewer allows us to view all of the devices in the Home Graph within the extension. Test Suite is a public tool that allows us to self-test and validate our smart home implementation. The Test Suite automatically generates and runs test cases based on the devices and traits associated with our project. Let's utilize the Test Suite on our virtual device. In the Developer Center console, we navigate to the Test tab on the left menu. In the device settings to the right, we click on the Test button to launch Test Suite. The devices associated with our project are listed in the resulting screen. We select our light bulb. We confirm the test cases will run and start the process. Test Suite then generates test cases for the selected devices and executes the tests. Failing tests will be marked in red. In our final exploration of the Matter development process and tooling, we will create a new device type. We will do so by editing the ZAP file previously used to generate our virtual device and change the device from a light bulb to a Matter sensor which measures temperature. A ZAP file is a JSON file that contains the data model configuration of clusters, attributes, and commands that are enabled for an application. A ZAP file can be created using the ZCL Advanced Platform or ZAP tool. The Zap tool is a third-party tool offering a generic templating engine for applications and libraries based on the Zigbee cluster library. This tool is included in the Matter repository as a submodule. We begin by launching the Zap tool from the command line and providing the lightbulb Zap file as an argument. The Zap tool may be launched directly or from Chef with the appropriate flags. The Zap tool's Zigbee cluster configurator window appears. We don't need to make changes to endpoint 0 as it contains the root node. The temperature sensor will also contain the root node with the same information. We select the Edit button of endpoint 1. In the dialog that appears, we select Matter Temperature Sensor 0x302 and click on Save. The required clusters for the temperature sensor device will be selected on endpoint 1, but confirm in the specification the right configuration for your device type. Some clusters, attributes, and commands are optional, and there are changes in the specification that might not be reflected in the tool. Moreover, feature flags should reflect the capabilities of your device. We set the filter to Show Enabled Clusters. Now, the list only contains the selected clusters. We click the blue gear icon to edit the cluster's attributes and commands. You may edit whether a cluster server or client is individually enabled by selecting the Enable column. You may also set Show back to all clusters and individually add or remove clusters to or from this endpoint. In the upper left-hand menu, we select File, Save As. We save the configuration file in examples/chef as temperaturesensor.zap and exit the tool. We have now created a new Matter device type. Now that we have completed the creation of a new device type, we can step back through the previous sections of the code lab and iterate on our design. We may start by asking the Assistant emulator for the reading of the sensor in the Google Home extension for VSCODE, or by executing the array of tests already available to us in the test suite. To iterate on our design further, we may relaunch the Zap tool, update our device, and rebuild it. This concludes our exploration of the tools.
Specifically, the smart home just doesn't work yet. Users are frustrated understanding whether a new smart home device is compatible with the devices they already use every day. And even if they can interoperate, integration setup is complicated and inconsistent. The underlying issue driving this problem is a connectivity protocol fragmentation that enables these devices to speak to each other, with competing protocols vying for adoption by users and device makers. Device makers are particularly challenged since they need to manage cost and time to market to support these protocols that users want. And in many cases, the stacks are lightly differentiated but require engineering resources to build, making it hard for them to invest in deeper feature differentiation to unlock more value for their users. CHIP intends to solve this problem with a protocol that can be integrated into smart home products that we hope can be widely adopted. It provides baseline connectivity for discovery, setup, and control of smart home devices. With this baseline connectivity, as an industry, we can give users the choice to have these devices interoperate in the way they want. To show compatibility and reduce purchase frustration, a CHIP brand and marking will be used on products. We founded CHIP with key industry partners in the Zigbee Alliance in December 2019. The team's been hard at work at leveraging these technologies and learnings from the past decade with IP as a centerpiece of the standard, which allows us to truly have an Internet of Things in the home. The new standard intends to improve smart home interactions in 3 key areas. The first is around baseline setup, where the underlying technologies support QR codes, BLE, and Wi-Fi soft AP to help with simpler onboarding and proof of possession during setup. The second is around interoperability, where device makers only need to support a single protocol to communicate with many ecosystems. Finally, reliability and security are improved with IPv6 being a core enabling technology in the protocol. Modern security practices are applied, such as certificate-based device attestation and PAKE-based algorithms for pairing. Since the kickoff in December 2019, we've had some rapid progress building the standard. For instance, we have 3 subgroups focusing on technical certification marketing areas and over 30+ teams driving their definition. This is a massive undertaking with over 160 organizations and over 1,000 individuals involved. The open source repository, which Don will be describing further, already has over 2,800 commits. The key devices for initial support have been selected in areas like lighting, access control, HVAC, and more. With all this hard work, we expect to land the specification and certification program launch by late 2021. And with that, I'll hand it over to Don to go into more detail about the connected home.
Hello, and welcome to our introduction to Project CHIP. My name is Don, and I'm a technical solutions engineer at Google Nest, focusing on IoT. If you're like me, The number of IoT devices in your home is growing rapidly. There are connected TVs, speakers, and now even appliances like refrigerators, washing machines, and stoves, all connected to the internet. Some devices connect directly to Wi-Fi. Most of us are familiar with how this works, since they connect to Wi-Fi in the same manner that you would connect your laptop, phone, and other devices you frequently use. Wi-Fi requires more power than other radio types like Bluetooth or Thread, and you'll notice that devices that make heavy use of Wi-Fi, like smart TVs, are typically plugged into the wall for a good source of power. Other devices, like your door lock and the alarm sensors in your windows, are designed to run on a battery for 2 to 5 years. Wi-Fi power requirements cannot be met here, and a low-power solution is needed. These devices use low-power radios and the IEEE 802.15.4 protocol to form a peripheral network, or a low-power and lossy network. This is what is used by Thread and Zigbee devices today. There are a couple of noteworthy differences between a Wi-Fi network and a peripheral network. First off, a hub is required to pass messages between your peripheral network and your Wi-Fi network and ultimately the internet. The blue lines here show peripherals connected to a hub, and the red line shows the hub's connection to the Wi-Fi router. A peripheral network can operate as a mesh to accommodate lower signal strength and expand the range of your network. In this example, the thermostat is routing messages between a light bulb and the hub. Although the thermostat is designed to be a low-power device, let's assume it's wired to the HVAC system power and has no design constraints preventing it from routing messages. Whether or not a device can route messages is at the discretion of the device maker. In this case, the lock could benefit from routing messages through the window sensor, but the window sensor doesn't perform routing since it needs to maximize its battery life. Devices like window sensors and locks are often called sleepy end devices. Project Chip standardizes on Thread for peripheral networks, which, among other things, uses IPv6 to communicate between devices. This provides a consistent, well-proven transport across your Wi-Fi, peripheral, cloud, and mobile networks. Alright, so let's dive into device development. Although the first stable version of the chip specification has yet to be released, the source code for Project Chip is public and available to everyone. This source repository is active, with frequent contributions for popular development boards and common device types. There is plenty to dig into to get a preview of chip device development, and you can run functional examples today. Remember, chip device development and ecosystem deployment are separate, which allows me to walk you through the basics of building and running a simple lighting application that could potentially be deployed anywhere. Project Chip is publicly available on GitHub, and it's released under the Apache 2.0 license. You can visit the link in this slide to go have a look. Within the examples directory, you can see a variety of different device applications with support for boards from Espressif, Silicon Labs, Nordic Semiconductor, NXP, and others. I'm going to give you a brief walkthrough of building and running the All Clusters app on an Espressif Rover kit. We'll be using it to demonstrate a simple on-off operation for something like a light bulb. If you wanted, you could use it to turn anything on and off using a GPIO pin. But today, we'll be toggling a virtual LED on its built-in display. Although this will not be a complete code lab, my goal is to familiarize you with the steps you'll be taking to get started, and show you how easy it is. You'll start with the building.md file in the docs directory. This will instruct you to install the build dependencies for your operating system, and to check out the source code. In this presentation, I'll be showing steps for a Linux workstation, but macOS is also supported. Next, you'll run a script to initialize your build environment. You'll see some nice ASCII art, some informational messages, and finally a message that you're ready to go. Before you build any device application, you'll want to build the chip client example, called ChipTool. You'll run this on your host machine to communicate with your device over the network. You'll find ChipTool within the examples directory, and will follow the instructions in the README. In many cases, Project Chip uses the GN Ninja build system, making build operations on the host as simple as what you see here. Next, we'll switch over to the All Clusters app directory, which is also under Examples, and then go into the board-specific ESP32 directory. Once here, the first thing you will do is install the toolchain for your Espressif board. Application developers have done an excellent job documenting exactly what to do to build a sample app for a board, right in the project chip repository. I've rarely needed to go to a manufacturer's website and hunt for information just to get started. It's all right there. For this application, Espressif requires you to check out their tools from their GitHub repository, set an environment variable, and run their install script. The All Clusters example supports multiple boards and pairing scenarios, so you need to configure it before you build it. When you run IDF make menu config, you'll be presented with a text interface to configure application options. Here, we've selected the Rover kit as the board that we're using. And since we're not pairing it to an ecosystem, we've disabled rendezvous mode and will specify the Wi-Fi SSID and password we want it to connect to. When configured this way, the device will automatically connect to our Wi-Fi network when it boots, and this will allow us to communicate with it without pairing it first. Note that this step disables critical security features, and devices should only be configured like this during development. Next, we'll build the application by running IDF make. To flash the application to your board, you need to connect it to a USB port on your workstation, and then run IDF make flash. And when you do this, you specify the USB TTY for the connected board. Once the device is flashed, power cycle it. If you connect a serial terminal to the same USB TTY, you will see logs as it boots up. The important thing to watch for is the message saying the server is ready and what IP and port is listening to. Finally, we'll use ChipTool, which we built earlier, to send commands to the device that toggle a virtual green LED on the screen on and off. The picture here shows you where to find the virtual green LED on the display. Note that when running ChipTool, we're specifying the IP address and port number we saw in the previous slide when booting the device. The device is also showing the standardized QR code for chip devices, which allow it to be paired using the camera on a mobile device in other pairing situations.